Hello everyone, good morning. So, here we are going to start our new unit with new chapter Energy Principles. In this case, first we have to understand about the energy. What is energy? And which kind of energy over here? That we have to understand first. In that case, in our previous subject, we have studied about the strain energy. What's that? What is strain energy? That strain energy is whenever we are going to elongate any body, it will be elongated. But whenever we are going to remove that force, it will be come back to its original position. Means due to elasticity, it will be come back to its original position, and that position will be gained due to the energy stored in that element. That energy is called strain energy. Means whenever our structure or element of structure is going to deflect, at that time energy will be stored in that element. Afterward, it will be come back to its original position. So, due to this energy, we are going to finding out the deflection and analyze our structure with the help of that strain energy, and it is converted in the principle of strain energy. It is done by the Castigliano's. This Castigliano's had finding out the different equations for the slope and deflection of the member, and after this, using this principle, he had developed another equation for analyze the indeterminate structure. So, this Castigliano's theorem is divided in two parts: Castigliano's first theorem and Castigliano's second theorem. In first theorem, he had given us the equation for finding out the slope and deflection of determinate structure, and in second theorem he had give us the equation for analysis of the indeterminate structure. So, here in first theorem, what exactly he going to describe us? That it states, if there any elastic system is in equilibrium under the action of set of forces W1, W2, W3 up to Wn and corresponding displacement delta 1, delta 2, delta 3 up to delta n, means whenever we are going to apply loads W1, W2, W3 up to Wn, at that time the deflection is occur under that load, and that is delta 1, delta 2, delta 3 up to delta n. And set of moments, whenever we are going to apply moments on the elastic body, that is m1, m2, m3 up to n, and the corresponding rotation, due to that moment rotation induced in our elastic body, that is phi 1, phi 2, phi 3 up to phi n, the partial derivation of the total strain energy due to this moment and due to this load, energy will be stored in our elastic body, and the derivation of that energy with respect to any one of force or any one of moment taken individually will give us corresponding displacement in the direction of action. Means, if we want to find out the delta 1, we have to take the equation that del u upon del w1. If we want to find out rotation phi 1, then equation is del u upon del m1. It will give us individual rotation and individual displacement. Now, this is the equation. Del u upon del w1 is equal to delta 1 and del u upon del m1 is equal to phi 1. Same way, del u upon del m2, it gives us phi 2, right? Now, from this, the Castigliano's first theorem is proven by him, and how it works. Consider an elastic body subjected to load W1, W2, W3, etc., each applied independently. The delta, the reaction at support Ra, Rb do not work while the body deforms because the hinge reaction is fixed and can't move. The roller reaction is particular in the displacement of the roller. Now, this is our elastic body. The W1, W2, W3 are acting due to this delta 1, delta 2, delta 3, and here somewhere rotation over here. Now, assuming that Hooke's law is valid, the displacement of the point of loading will be a linear function of the loads, let's delta 1, delta 2, delta 3, etc. be the deflection of the first point, second point, and third point in the direction of load at this point, that we know. Now, the total strain energy stored in the body, that is 1/2 of W1 into delta 1 plus 1/2 of W2 delta 2, same way up to the n, right? Now, let's the load W1 will be increased by amount of dW1. Due to this, there will be a small changes in deformation, that we know. Whenever the load is increasing, the displacement is also increasing, and this phenomena is understood by us in our previous lecture, previous subject in SA1. In that case, we have studied about the whole displacement and rotation chapter with the help of different methods like double integration method, Macaulay's method, and moment area method, conjugate beam method, even unit load method is also there. So, from that, we can understand that if we are going to increasing the load, the displacement is also increased, right? Now, the strain energy will be increased straightly at an amount of du, right? If displacement increased, then energy also increased. Now strain energy will be U plus del U upon del W1 into W1. Now total work done is dW1 is equal to dW1 into delta. The new energy stored, that is U plus del W1 into delta 1. Since the final strain energy does not depend upon in order to which force is applied. The equation 1 and 2 and 3 are using, and we will get the U plus del W1 into delta 1 is equal to U plus del U upon del W1 into dW1. So delta 1 is equal to del U upon del W1. Similarly, if phi is there, then phi 1 is equal to del U upon del M1. Okay. So we have this equation which is used to finding out the slope and deflection, and from that we will get our final equation, how it works for our particular beam element. It will be something like that, but the energy stored in our beam due to deflection is understood by us in our previous subject, structural analysis 1, and we have the equation for that. U is equal to integration 0 to L m square upon 2 Ei into dx. When m is the function of load P. Now, due to this, P force moment will be generated. That's why m is a function of load P. Here, for the deflection, the partial derivation of strain energy U with respect to P will be give us the deflection delta. Right? So, the equation for that is 1 upon Ei integration 0 to L mx into del mx upon del P into dx. This equation is important for us. Now, the partial derivation of strain energy with respect to m will give the rotation, means theta is equal to 1 upon Ei integration 0 to L mx into del mx upon del m into dx. This method is finding out the deflection and rotation, also known as the partial derivation method or fictitious load method. We know this is our fictitious load method, because whenever we want to finding out the deflection, we are going to assuming the P load as a fictitious load over there, and after that we will put the value of P 0 over there. Okay. Now, from the first we will get the idea about the how to finding out the slope and deflection for the determinate structure. Now, in second theorem, what he told that if we have any indeterminate structure, it will be having some SI, that is called ds, that we know. We will discuss in our previous subject fundamentals, and that ds is gives us some value, and that value is using in this indeterminate structure, and we will find some redundant, right? That redundant is very useful for the analysis of indeterminate structure using Castigliano's second theorem. It states that if U is the total strain energy stored up to the framework of the in equilibrium under the external system of the force, its magnitude is always a minimum. That's why it is called minimum or least work method. In this case, here we have the value of deflection at the support is 0. If U is the total strain energy stored in the body, the partial derivation of internal energy with respect to the load P applied at the point where deflection is 0 is also 0. So, del U upon del P is equal to 0. So, this is our one condition, and this condition is helping us out the finding out the unknown reaction more than the number 3. So, this theorem is also known as principle of least work theorem, as I discussed, or minimum strain energy. Whenever deflection is 0, the energy is stored 0. So, 0 energy or minimum strain energy we can call that. The structure will deform due to the applied load by the minimum amount of possible, so that work done on it or the internal energy stored in the minimum, right? So, dear students, these two methods is important for us to finding out the slope and deflection, and even it is used for analyze the indeterminate structures, right? Means we have 6 type of beam. First one is simply supported, second one is cantilever, and third one is overhang. These 3 beams are determinate beam, as we know, and that determinate beam is used in Castigliano's first theorem for finding out the slope and deflection. Now, remaining 3 beams are fixed beam, propped cantilever beam, and overhang beam. These 3 beams are indeterminate beam, and that indeterminate beams are analyzed using Castigliano's second theorem. In that case, from we have equation that total strain energy and the partial derivation of that energy with respect to load is equal to 0, means delta is 0. So, due to that equation, we will get some unknown reaction, right? And that unknown reaction is used to finding out the shear force and bending moment for particular indeterminate structure. So, Castigliano's theorem is gives us the idea about the whole structure to finding out the slope and deflection as well as analysis of the structure. So, here we have to clear idea about the how to finding out the moment at x, and we have to take segments for the different methods, different parts of the beam, and here we are going to integrate the moment with respect to fictitious load P, or else unknown reaction as redundant. So, our mathematical step regarding to this differentiation as well as integration is very much strong for the analysis of this method. So, in next lecture we are going to understand about the how to finding out the slope and deflection using Castigliano's first theorem. After that, we will finding out the another determinate beam. Okay. So, here we have the equations that del u upon del p is equal to 0, u is known by us, right. Same way del u upon del p is 0, right. So, these things will increase our knowledge towards the analysis and slope and deflection. Thank you. In next lecture, we will discuss about the examples. Okay. Thank you.